Welcome. My name is Chuck Ridgway. I'm the Automation Technology Manager here at Horner, and I'm pleased that you're joining us today. Today, we think we've got a great program for you. It's a continuation from a topic that we started last week, but this week's topic is CsCAN Networking, Installation and Troubleshooting. So last week, in part one, it was all about CsCAN Networking, how it works. CsCAN is a proprietary Horner network that we invented many years ago for some high-speed material handling applications. And last week, we spent plenty of time talking about how it works. And this week, it's going to be all about installation and troubleshooting. So joining me today is my colleague, Mr. Casey Gardner. How's it going, Casey?
Hey, not too bad. How's it going, Chuck?
It's going great. Hey, I'm sure over the course of your career here at Horner, in the process of setting up your own CsCAN networks as well as helping customers, you've probably experienced a few things that can trip you up. What are some of those things you've run into over the years?
Oh, yeah, there always seems to be something, I think probably most common, or at least ones we don't always think about, are going to be things like baud rate. Make sure it is what you're expecting it to be. Having terminating resistors and making sure they're actually seated in the way you think they are. Making sure your rotary switches on your I/O modules are where they think they are, that kind of thing. So there's definitely a number of different things, and I know your presentation's got way more than that included in it too.
All right. Yeah, I think it'll be informative. One of the great things about CsCAN is it's really straightforward. And for most applications, let's say 99% or let's say 90% of the applications, if somebody's using CsCAN, they're probably expanding I/O locally, maybe even in the same control panel where the OCS is mounted. So in that scenario, there's really not much to it. It's really pretty straightforward. Now,
Absolutely.
Yeah, but in those scenarios where it's a little more advanced, maybe you've got multiple OCSs distributed over a long distance, maybe a lot of nodes, when the distances increase, when the number of nodes increases, that's where you got to watch your P's and Q's a little bit. And with today's presentation, I think hopefully that'll prepare customers who are looking to expand their use of CsCAN. It'll give them the information they need. Okay, let's go ahead and dive in. Okay. CsCAN Networking, installation and troubleshooting. Here's kind of the layout of our topic for today. We're going to do a quick review for those of you who weren't with us last week. Just going to spend one slide to talk about it, but we want to make sure that if you didn't attend last week, you understand what we did cover, and we'll get you caught up to the point where the fact that you missed last week doesn't affect your ability to take in this week's presentation. We're going to talk about network architecture. We're going to talk about some of the network limits in terms of how many nodes can be in a network and how long those networks can be. We're going to review the pinout, of course, what kind of cabling you should be using. We're going to talk about power distribution, because with CsCAN, you have the ability to power your I/O nodes from the network directly. We're also going to give you plenty of troubleshooting tips. So hopefully this is a pretty comprehensive coverage of the topic, and you get lots of good information out of it. All right, let's get started with a quick review. So last week we introduced CsCAN, and CsCAN is a proprietary Horner network that's built on the CAN chip. Okay, so the CAN chip is the hardware that CsCAN is built upon. Now, we originally designed CsCAN for high-speed material handling applications, especially a really large project that we did with the U.S. Postal Service. And after last week's presentation, Phil Horner called to remind me that CsCAN was out and about before either DeviceNet or CANopen were available in the marketplace. So it's been around quite some time, but it's still relevant today. It's got a lot of great characteristics, including a purely peer-to-peer data exchange, so it's not a master-slave protocol at all. You can certainly program over the network, and we demonstrated that last week by physically connecting over Ethernet to an XL7, and then connecting that unit over CAN to an XL4 and being able to program both units. So you can certainly program over the network, something we call single point of connect. And also, CsCAN is certainly the easiest way to add I/O to any OCS. Another thing we covered last week is that from a data exchange standpoint, CsCAN is based around global data outputs. And every node on the network has 32 words of global data output along with 64 bits of global data output. And if that's not enough for a particular controller, if you need a particular controller to generate more data, you can do that. You just need to assign multiple consecutive node numbers to any particular OCS on the network. And then if that's the case, then you can literally multiply that amount of data. So that should get you caught up. Again, CsCAN is a peer-to-peer network built on the CAN chip. Global data is exchanged. Typically, when you're talking OCS to OCS communications, it's really just a simple matter of I/O configuration when you're adding I/O to an OCS controller. Okay, so let's get into today's topic. The first thing I want to cover is the network topology. Now, CsCAN is typically implemented in a daisy chain type fashion, where the network cable is run from node to node to node, and at the two ends of the network, you have what's called termination, and we're going to cover that more later on in the presentation. Now, an alternative to the daisy chain topology, which is equally as valid, is a trunk line, drop line approach, where you have a network that is effectively a trunk. You have devices called T's at every location where you want to locate a node, whether it's an OCS or an I/O block. And then you have a drop line that connects that node and the T. And typically your trunk line is a fairly long distance, and your drop lines are just short little drops, typically from the outside of the panel to the inside of the panel. So those are the two topologies with CsCAN. Daisy chain is certainly the more common of the two. For those who use trunk line and drop line, it's very common for them to utilize accessories like T's and other type M12 type circular connectors when they're implementing that particular network. And there are some advantages to that. We'll talk about that later as well. All right, so we've talked about topology. Now let's talk about the network limits. What are the maximums allowed on the network in terms of number of nodes and in terms of total distance? So from those two factors, with CsCAN, you can have up to 253 nodes on a single network. Now, you're typically not going to have anywhere near that many. Usually it's just a few. But on that large post office project I talked about, we had several networks with well over 100 nodes per network. So it certainly has the capability of expanding up pretty well. Now, in addition to the limit of 253 nodes per network, you're limited to 64 nodes per segment. Now, what is a segment? We'll talk about that in a second. In terms of total network distance, you're limited to 2 kilometers or 2,000 meters per network, but no more than 500 meters per segment. What do we mean when we talk about a segment here? Okay, well, let's take a look at this graphically. What I'm showing there in that diagram is 4 interconnected segments, each that have to be 500 meters or less. Each has to contain 64 nodes or less. Those are all interconnected using up to 3 repeaters. So if I've got an application with just a few nodes, far less than 500 meters, then I'm only going to need 1 segment for my entire network. There's no reason for any kind of repeater in almost any situation. However, if my number of nodes exceeds 64 or my network distance exceeds 500 meters, now I can add a repeater and I've effectively doubled my network distance. And as you can see, the maximum there are 3 repeaters for a total of 2 kilometers in length and 253 nodes total. Now, what is a repeater? Well, a repeater is a device, a specialized device, that has 2 CAN connections on it. It has a network in connection and it has a network out connection. And a repeater accomplishes a variety of things, 2 primarily. One is it provides electrical isolation between the 2 networks. And secondly, it also effectively adds a completely new network in terms of nodes and distance to the system. So it will literally accept in the messages that come in through the first network connection and then rebroadcast those messages as is on the second network connection. Again, I want to stress that most applications are far less than 500 meters or far less than 64 nodes, so you don't need a repeater. But when we're talking about network limits, we need to talk about repeaters. One other thing I will mention, and that is not all repeaters are created equal. So today, there's a specific repeater from B&B Electronics, which was acquired by Advantech, which we recommend. So certainly if you have a need for a repeater in a CAN application, in a CsCAN application, don't hesitate to contact us and we will reference that specific CAN repeater to you. All right, so we've talked about topology and the limits in terms of node addresses and distance. Now let's talk about cabling, because one thing that a lot of people do not realize is that with CsCAN and CAN in general, you really need to use specific cable. You can't just use any old twisted pair that you might use for Modbus RS-485 with a CsCAN network or a CAN network in general. So for CAN-specific cabling, there are 3 types which are commonly used. And they vary in terms of their construction, in terms of the gauge of the wire that's included, and they also vary in terms of the distances and the baud rates which they can support. So let's start with thick cable. Now, thick cable has the heaviest conductors. It's got 18 and 15 AWG pairs for data and power, and it's pretty thick. How about that, huh? Not real flexible, so it can be a little challenging to work with sometimes. So certainly, you're only going to use that cable if your network distances are significant. Now, a slightly easier to work with cable with conductors that are a little less rigid would be mid cable. It's good for up to 300 meters. I've used that on a couple projects, one recently, and actually I was pretty happy with it in terms of how easy it was to work with. But most applications will be perfectly fine with thin CAN cable, which is good up to 100 meters. And it basically is 2 twisted pairs, a 24 gauge and a 22 gauge. Again, specially constructed, not just your run-of-the-mill 2 twisted pair type Belden wire. It's specifically Belden 3084A, as you can see on the screen there, along with the Belden numbers for mid and thick. So you do need to use special CAN cable. Now there's an exception to that, and that is today what you'll find is that more and more unshielded LAN cabling, Cat5, Cat5e, is being used in CAN applications. And we currently are doing some testing. Casey's actually one of the folks that are leading that effort. We're currently doing some testing so that we can set some length limits as well as baud rate limits and node limits and that sort of thing for those customers who want to use Cat5 for CAN. But until we complete that, we are making a fairly conservative recommendation today, and that is if you have an application where the CAN network never leaves the control cabinet, you're just adding I/O locally, for instance, you've got 8 drops or less, then go ahead and use Cat5 cable. No reason to buy special CAN cable in that instance. And you can continue to use standard termination just as if you were using specialized CAN cable. Now, the special CAN cable is 120 ohm impedance. That's the characteristic impedance of the cable. Most of you probably know, or some of you probably know, that category rated cable, Cat5e for instance, has 100 ohm of impedance. So don't let that difference worry you in terms of termination. You can use the same termination approach and the same termination resistors in either case. And again, later on this year, when we complete our testing, we'll publish some longer limits in terms of network lengths, the number of nodes, and those sorts of things. But for now, those are the limits that we've set officially. Now, one of the nice things about using CAN cabling is that it's color-coded. So with CAN, we haven't covered pinouts yet, that'll be next. But with CAN, you've got the cabling that you use is nicely color-coded. So that makes it easy to match up the right conductor on the terminal strip or whatever the connector is that you're using in the application. And really the same is true with category cable as well, because those, of course, are standard pairs and standard colors. So we can publish what those colors should be if you're using category cable as well. So those are the color codes. Let's start talking about distance and baud rate. Now, last week we talked about the fact that increasing your baud rate does not buy you a faster update rate. It buys you more bandwidth. Well, what do we mean by that? Well, here let me explain. It basically takes, at 125K baud, it basically takes 1 millisecond for a CAN message to travel the wire. At 1 megabaud, which is the maximum baud rate, it takes about 1/8 of a millisecond. Now, the OCS is only going to really update its network connections. It's only going to update that once per logic scan. Let's say every 5 milliseconds if that's your logic scan. So that's plenty of time for that message to be handled in between scans. So you're not going to notice any difference from an update rate standpoint between 125K and 1 megabaud. However, what speeding up your baud rate does do for you is it does give you the ability to have more messages per second or more bandwidth on your system. Now, let's face it, almost all the time, 125K is going to work perfectly fine. So almost all the time, there's really no reason to bump that up beyond the default. But if you decide to do that, the reason you would is because you're looking for more bandwidth, not because you think you're going to get a faster update rate in the controllers. So another thing you'll notice from that table on the right is that as you speed up your baud rate, you are dropping the amount of distance that you can support, to the point where if you're using 1 megabaud, you're limited to 50 meters total. Another thing to keep in mind is that smart sticks and smart block I/O are only good for 125K. They will not work at higher baud rates. You can't even set them at higher baud rates. Whereas smart rail, you have flexibility. You can set that using a dip switch under the cover. So again, 125K is by far the most flexible, and there's seldom a reason to bump that up. All right, now let's start taking a look at the terminal strips, at the pinouts. And we offer some different approaches to connectors depending on the product you're using. Let's start with terminal strips or open connectors. These are the types of connectors that you'll find on the XLE and XLT. You'll find those on every product from the XL4 on up. You'll also find it on smart sticks, smart rail, smart block. Okay, it's a 5-pin terminal strip. Now with some products, like the XLE and XLT and the smart rail and the smart sticks, it's what we call a single block, the one there at the left. Okay, so there's one point to land your wires. Okay, if you have network in and network out, you have to land that on that one set of terminals. Now other products, everything from the XL4 on up, as well as the smart block, they feature a double plug. That gives you conveniently 2 locations to connect. Network in and network out, or a dedicated place to drop a termination resistor if you happen to have a node that's at the end of the network. You can also buy that double plug as a separate accessory, and I definitely recommend that for an application where you're using, let's say, smart sticks or smart rail, or even the XLE and XLT. I would strongly consider the inexpensive accessory that is the double CAN plug. Okay, and as you can see, you can easily line up the color code for the CAN cable you're using with the particular terminal on the connector. Another option you'll find is for those folks who are looking at a trunk line and drop line approach, which I talked about earlier, you've got the ability to use circular connectors or sealed circular connectors, typically M12. And with these, you have the same 5 conductors, if you will, okay, except they're connected to a sealed connector. And either you're going to be purchasing a field wireable sealed connector and doing the wiring yourself, or you're going to be purchasing a pre-molded cable. And obviously one of the benefits of the pre-molded cable is that, in theory, it takes away wiring errors pretty much from the equation. So as long as the cable that you purchase does the job and was manufactured in a quality fashion, it should greatly reduce the odds of a wiring error in your system. We also have a pretty nifty accessory that can convert any Horner product that has a terminal strip into a sealed connector. You'll see that there on the right. And those are very popular. We sell a lot of those. And finally, we also have plenty of products, especially newer products, that feature a modular connector or an RJ45 jack. So you'll see those on the entire Micro series, the X2, the X4, the X7, and the new X10. You'll also see it on the upcoming OCS I/O, and I'm kind of teasing you with a little circular shot there on the left showing the OCS I/O and the input and output connections that are featured for the network. So that is something that you'll see on the OCS I/O when we get that released later this year. And then on the right there, you can see that the standard color codes for Cat5 will apply to these particular connectors as well. Now, let's take a look at that particular pinout. Now, normally with the RJ45 type connectors, normally you're not powering anything over the network. Normally it's a scenario where, or if you are powering something, it's one I/O block or something very minimal. Typically, you're not connecting the V+ power connector. We'll cover power in more detail later. You're typically just connecting the communications pair, which is pins 1 and 2 on the RJ45 pinout, as well as the network common, which is pin 3 or V-. So that's the RJ45 pinouts there. And one of the nice things about the RJ45 pinout is that once we release OCS I/O, you'll be able just to use regular old Ethernet patch cables to interconnect an OCS and OCS I/O, certainly within a cabinet without any problem whatsoever. All right, next let's talk about termination. I kind of hinted at this before. So what is termination? Anytime you have a daisy chain style network such as CAN or RS-485, you have the potential for reflections of the signal that can be bouncing around on the network that can cause errors and prevent good communications. All CAN networks must be terminated regardless of length. So if you're setting up a CAN network at your desk, you need to terminate it, okay? It doesn't matter that it's 1.5 feet, you still need to terminate it, okay? If it's 500 feet or if it's 1 foot, you need to terminate it. Now for an open style connector, especially if you're using the double plug, it's really easy. You can just install the 121 ohm resistor across CAN high and CAN low. Now you may be saying, where in the heck am I going to get a 121 ohm resistor? Well, the good news is every OCS product, every OCS controller ships with 2 120 ohm resistors, because typically you're going to be installing I/O or other devices to the OCS. So we supply those resistors with the OCS itself. So you should have, as long as you've purchased an OCS, you've got all the termination resistors that you should need. If you don't happen to have them or you've lost them, you can get more from us, or you can purchase them, of course. They're basically just 121 ohm, I believe, 1% accuracy type resistors. Okay, if you're using products with modular jacks like the X4, X7, X10, X2, okay, well, you can locate a physical resistor somewhere near the controller on a terminal strip or something, or more easily, you can actually go to the system menu and set the termination option on from the system menu. So that's an option for all the Horner products that have modular jacks. And then if you're using a sealed connector, like an M12, then when you are purchasing your T's and your extension cables and your network cables and those sort of pre-molded cables, another option you can purchase are terminating resistors, prepackaged with either a male or a female M12 connector to make it easy to add to either end of the network. And once again, termination is added at both physical ends of the network, all right? Not on the OCS every time. It is added to the OCS if the OCS is at the end of the network, but if the OCS is in the middle of the network and there's just I/O on either end, you're going to terminate at either end. All right, now let's talk about power management. Power management is a topic that requires a bit of care. One of the advantages of CsCAN is it is one of the networks that is designed to provide power, DC power specifically, over the network from the V plus and the V minus pair. So that does a couple things. One thing it does is it adds a level of isolation between the field devices and the logic devices, because typically at least, CAN is going to be isolated from the digital inputs and outputs that are connected over the network. It's not always true, but it's often true, especially with the XL series products, Smart Rail, Smart Sticks, etc. So power is available over the network, and it's typically at 24 volts, although with voltage drops and things, it could go down to say, 15 volts even. But 24 volts is the nominal network voltage. All OCS controllers are not powered from the network. So all OCS controllers, and this includes RCCs and other controller products, they all get their power from a dedicated terminal strip, not necessarily from the CAN port. Now, there's one exception to that, I believe, and that is the RCC 6512, which is our high-speed coprocessor. It's the only controller that we sell, to my knowledge, that does get its power from the network. Every other controller we sell does not get its power from the network. Now, from a CsCAN I/O standpoint, all CsCAN I/O, whether it's Smart Stick, Smart Rail, or Smart Block, does get its power from the network. Now, that's not necessarily the power to drive outputs, okay, but it is the power to power the block and power the circuitry internal to the unit. The power to drive outputs, motor starters, etc., that must be provided separately through a separate terminal connection. But the power to power the I/O block always comes from the network. Now, here's a couple rules of thumb. If your network leaves the OCS control cabinet, so it's expanding beyond the cabinet which the OCS is installed, and you've got CsCAN I/O attached, we typically do recommend you have a dedicated power supply. Do you absolutely have to have it? No. Do we recommend that you have it? Yes. Especially as you add more and more I/O or more distance, there are certainly advantages to having a dedicated network power supply for sure. Another good rule of thumb, if your network length exceeds 30 meters, or you have 4 or more I/O nodes, you really should do calculations on your total current draw as well as your voltage drop calculations, so that you don't end up with a situation where you have excessive voltage drop and then the I/O that is powered from the network doesn't have enough voltage to operate, or a scenario where you're drawing too much current from the network. Either of those would be bad. So if your distances are less than 30 meters and you have less than 4 nodes of I/O, don't even bother with the calculations. If you meet that standard, then go ahead and make the calculations. And I'll go ahead and show you a little later on, the method you're going to use to make those calculations. Let's talk about maximum allowed current, because we're providing power on the network or current over the network to drive I/O devices does not mean it's an infinite amount that's allowed. Regardless of the CAN cable you're using, and I'm talking about dedicated CAN cable now, the thick, thin, or the mid stuff, most electrical codes restrict you to a maximum of 4 amps. So even if the gauge of the wire exceeds 4 amps in terms of capacity, from an electrical code standpoint, that doesn't matter. 4 amps is the maximum as far as they're concerned. So that's something to be aware of. Now let's talk voltage, minimum voltage. As I mentioned, the network power is 24 volts typical. But of course, the further you get away from the power supply, you're going to have voltage drop. Now, CsCAN nodes will operate all the way down to 12 volts DC. But from a recommendation standpoint, you should really target 15 volts or higher to ensure that you don't have a voltage issue with your network. Next, let's talk about the network power supply location. If you do have one of those applications where you need a network power supply, your network's longer than 30 meters, you've got more than 4 I/O nodes, in that scenario, then the best case scenario would be to locate the power supply in the middle of the network, not on an end. That's optimum. Now you can do the calculations for voltage drop and current draw, and you may find there's no problem in locating the power supply on one end. That may be the most convenient and may otherwise have no issues. Just be aware that the optimum location is in the middle of the network. That way, you can supply potentially 4 amps to the network that's, let's say, below the power supply, and 4 amps to the network that's above the power supply. And then you won't violate the 4 amp requirement. It'll also help with voltage drop. Again, in a large application, it's the optimum scenario. So, how do we calculate voltage drop and current drop? Well, let's start with voltage drop. Let's start with what we need to know. What do we need to know in order to calculate our voltage drop? Well, the first thing we need to know is the resistance of the network cable. So when you purchase CAN cable, whether it be thin, mid, thick, there's a data sheet that's available for the cable that very clearly spells out what the resistance per meter or resistance per 1,000 feet is. So you can use that resistance level to help you calculate your voltage drop. And we'll give you the equation in the next slide. Another thing you need to know is how far is each node away from the power supply. That tells you how much wire is between the power supply and that particular node. Now, one thing to keep in mind about network distance is that, or resistance, if you will, is that the current has to travel up one wire and back another. So you're effectively either doubling your resistance or doubling your distance for the next calculation we'll make on the next slide. So just one thing to keep in mind there. But again, you need to know the resistance for the cable, and then you need to know the distance from the network power supply. A couple more things you need to know. How much current is that I/O drop going to draw? And you can find that in the data sheet for the I/O module that you're using. Using SmartSticks I/O, no problem. Just look up the current draw for that particular I/O module. It'll give it to you right there in the data sheet. Another thing to know, how many nodes are in between the power supply and the particular node that you're calculating for voltage drop. So if I'm node 7 and they're numbered sequentially 1 through 7, and I'm calculating the voltage drop for number 7, I know that there are 6 nodes in between that particular node 7 and the power supply. So that's an important piece of information as well. Now let's take a look at the equation. And don't get all worried about this equation. It's not that bad. Really what you're going to do is just like everything else in electrical engineering, you're going to go back to V equals IR. Voltage equals current times resistance. So what we're going to do is we're going to take the node current, the amount of current that that particular node is drawing, and we're going to multiply by the total resistance that that node sees between itself and the power supply. So what is that total resistance that's seen by that node, between that node and the power supply? Well, it's affected by the cable resistance times 2. Why times 2? Well, again, the signal has to travel up one wire and back again. So the distance is effectively doubled. That's why we have 2 times the distance to the power supply times the resistance of the cable. And then we add to that what could end up being just another really small amount of resistance. And that is the fact that every time you break a network or you have a node on the network, the terminal block where you're connecting the 2 parts of the network has a little bit of resistance to it. And we're going to make an assumption that that's about 0.005 ohm. And again, we're talking about scenarios now where you've got a large network, and we're going to make sure we're doing this accurately. So that's where you would use how many nodes between me and the power supply. I'm going to take that number, multiply by 0.005 ohms per drop, if you will, and that will add to my total resistance. And then I'll take my node current times my total resistance after I've calculated that, and that'll be my voltage drop. Looks more complicated than it is. I typically put it in a spreadsheet, and in no time I've got all the calculation I need. All right, so we've calculated voltage drop for a particular node. Now, how do we deal with current draw? Okay, well, we start by calculating voltage drop on each node, starting at the node that's closest to the power supply, and then we kind of work our way down away from the power supply. Keep this in mind. The power required to drive each node on the network is constant. So let's say I have smart sticks. Let's say I have 3 identical smart sticks, and they draw 125 milliamps at 24 volts for a typical operation. So if my voltage at that smart sticks is 24 volts, I know that my current draw is 125 milliamps. But let's say that smart stick is located, a couple hundred feet away from the power supply, and the voltage at that particular smart sticks, let's say, is 20 volts. All right, well, it's going to need to draw more current to get the same amount of power when its voltage is only 20 volts instead of 24. So the further you get away from the power supply, the higher that current is going to be for each node as you move away from the power supply. So we start by checking the voltage drop at each node. Using that voltage drop information, we calculate the current that's going to be drawn by each node as we move away from the power supply. And then as we get to the end, we want to make sure that our voltage never dropped below 15 and that our current never exceeded 4 amps. So that's really all there is to it. Again, it sounds more complicated than it is. Use a spreadsheet and you'll have it in no time. Now, what happens if current does exceed 4 amps at any point on the network? Well, if your power supply is not in the center, try moving it to the center. That should break up the current to the point where on either side of the power supply, you should be below 4 amps. If that isn't good enough, in other words, that didn't help enough, then you'll need to add an additional network power supply to the network. So, compared with the other topics, we spent quite a bit of time talking about power draw and talking about voltage drop. Now, keep in mind that for most CsCAN applications, you're going to be below 30 meters, you're going to be below 4 or 5 I/O nodes, so all those calculations or none of those calculations will be required. But again, I want to give you the tools so that if you do take advantage of this great capability of CsCAN for longer networks and more nodes, that you'll know how to do it. Now, let's talk about wiring the network. We've planned our installation. We've calculated what our voltage drops will be. We know we're not exceeding any of our limits in terms of nodes or distance. We've got the right wire selected. We've done all this planning. Now we actually need to install. What are some things we need to know when we're installing? Okay, let's start with power supply wiring. If there's a good earth ground near your network power supply, you'll want to connect V- at that point to earth. V- should only be connected to earth at one point only. And again, if that location of the network power supply happens to be a good earth ground location, ground it there. If it's a lousy location for earth ground, well, find a better location for earth ground and ground it only there. Again, it's very important that earth is connected to V- at only one point. Now, what about the scenario where you need multiple power supplies? How does that work? Remember, the reason we need multiple power supplies is because we're exceeding 4 amps on a particular segment, and we couldn't get around it by just moving the power supply around. If multiple power supplies are required, you're going to connect the V- or the black wire between power supplies. Okay, so that'll be continuous on the entire network. The V- wire will be continuous on the entire network. Now, the V+ wire, on the other hand, the red wire, should be disconnected between power supplies. So one power supply will be powering a particular segment of the network. Its V+ will be connected to all the nodes on that segment, and it'll be disconnected from any other nodes. Same thing for the other power supply. So that's another network wiring tip. Next, let's talk about the shield. Now, when CsCAN was first released, there was an original method which we, along with other manufacturers of CAN networks, recommended in terms of shield handling. That method was, for every piece of wire between two nodes, you would always earth ground one side of that piece of wire and not the other. And that's a perfectly legitimate approach, and many of you may have CsCAN networks that were installed that very way. And that's fine. There's nothing wrong with that per se. The problem is, it can be difficult to keep track of which side of that particular segment of wire is actually grounded and which one isn't. And you end up with multiple locations for ground, and it could be complicated to figure out. So, to make things easier on everyone, we now recommend another method, and that is where you effectively create a continuous shield. All your shield drains are connected to each other throughout the network. You could connect them to each other by landing them on the CsCAN plugs. That's perfectly fine. Make those shield drains connected to each other on the entire network so that now you have effectively a continuous shield. Now, what about grounding or earthing of that shield? Well, you're only going to connect the shield, that new continuous shield, to earth at one point only, preferably near the power supply if that's where V- is earthed, for instance, and you're going to want to ground it with at least a 14 AWG conductor. Okay, so once again, create a continuous shield by connecting all your shield drains to each other on the entire network, and then ground the network at one point only, preferably near the power supply if that's where V- is earthed. Let's talk a little bit about V+. Now remember, V+ is required if you are going to be powering a node from the network. So if you're talking about an OCS, whether that's a microseries product or a OCS, let's say an XL4 or an XL7, there's no requirement for the V+ to be landed on the terminal block for an XL7, XL4, etc., any OCS for that matter, because it's not actually using that terminal for itself. However, there's absolutely no disadvantage or there's no harm in connecting V+ to the terminal strip. And I would recommend you go ahead and do it. All right, so just run V+ everywhere, connect it neatly so every node is wired the same, and then that'll be the easiest to deal with. But again, OCS nodes aren't going to actually draw any power from that pin. Now, what some customers will do is they'll use that same approach with V-, which is the black wire. That absolutely won't work. The V- wire must be landed at each node, whether it's an I/O block or an OCS, it doesn't matter. Okay, this pin is required, or this lead is required to prevent common mode voltage issues, which certainly can occur on networks, especially longer networks. So you must land the V- conductor if you're installing the network on every node, regardless of whether it's an OCS or an I/O block, whereas the V+ connector is technically optional, but we still recommend that you daisy chain it and make it complete through the network as well. Okay, now let's talk about troubleshooting. All right, we've done our planning. We've installed everything per the recommendations I just reviewed in terms of how we handle the shield, how we handle the power supplies, what we do with V- and the fact that we earth it at one location only. We followed all those guidelines. Now let's talk about some troubleshooting. And these are not necessarily troubleshooting steps that we would only take if we're having trouble. These are troubleshooting steps we should take on every installation of any significance. All right? First thing we should do is we should check the termination on our network. Remember, we should have a 120 ohm resistor, whether that's a physical resistor or just a turning it on in the system menu for a microseries product, but we should effectively have a 120 ohm resistor at both physical ends of the network. So we can power down the system, use our multimeter, and check the resistance across CAN high and CAN low, and we should get somewhere around 60 ohms, because remember, 120 ohms in parallel with two resistors should give us 60 ohms. If it is 60 ohms or thereabouts, we're good to go. We verified it. That's great. But what if it isn't? Well, if our reading is above 120 ohms, it means we probably don't have a termination resistor installed. Or if it's exactly 120, it means we probably have one installed and not the other. Well, what if it's, say, above 60 or 70, below 120? Well, in that scenario, we want to check for an open circuit, all right, between CAN high and CAN low. That's a clue we might be having an open circuit there. Well, what happens if our resistance across CAN high and CAN low is below 50 ohms? Well, that could be an indicator of a short circuit. So it's really a good idea to check your termination, even if you're not having trouble. And let me give you another reason why it's a good idea. CAN is extremely forgiving. For those of you who attended last week, you probably remember me saying that CAN was developed to work in very harsh environments, not necessarily environmentally, because it'll handle that too, but electrically. So you could have some things wrong with your wiring and it still might work. But you want to find those things and correct them so that long term you don't have any issues. So that's the first step. Power down the system, check your termination with your multimeter. What else should we do? Remember, in the installation steps, there were two things I said in terms of earth grounding. I said earth ground V- at 1 point only, preferably near the power supply, and earth ground the shield at 1 point only, preferably near the power supply. So that means there's exactly two places where earth is connected, V- and shield. So what you should do after everything is connected is go ahead and disconnect those two connections to earth, and then use your multimeter to check the impedance between your conductors and earth ground. And you should see greater than a mega ohm, because you should have an open circuit at that point. If you have less than a mega ohm, especially if the resistance is low, that tells you that somewhere else you're unintentionally connected to earth, and that is not what you want. So with your two earth points disconnected, you should have greater than 1 mega ohm. Once you measure that, you have confidence that once you reconnect those 2 points, those will be the only points at which you're connected to earth. Okay, another thing you can do, or should do absolutely on every installation, is you can go to the OCS system menu and take advantage of some of the diagnostics that are available there. The first thing that's available is CAN OK. That is something that you can check in the CAN settings under network configuration on the system menu. That obviously should be okay. Also, in the status menu, again available from the system menu, there are a couple of statistics that you can monitor. One is local network usage, and the other is all network usage. Now, those are percentage type statistics, and they are, they're going to be giving you anywhere between 0 and 100%. So you should take a look at those and see if the number looks reasonable. Does it look reasonable or not, given on what you know about the potential, network traffic that's happening there? All right, so this is where I'm going to actually show you something live to try and give you an idea of the way that using this particular feature in the system menu could give you a clue that you might have a problem. I'm going to go ahead and pull up the two controllers that I had last week. I'm going to pull those up on my screen. Let me go ahead and do that here. So we are looking at a EXL6 and a XL4. And by me putting my hand in there, I made my autofocus hunt a little bit. Sorry about that. Okay, so what's happening in this very, very simple application that we showed off last week is on the EXL6, we are writing 1 bit of data to the network, which is just a push button. And then we're also writing 1 word to the network, which is just a word of changeable data, and then it shows up on the other side. I just mentioned that one of the things we want to do when we're troubleshooting or after we install a CAN network is, in addition to checking things with our multimeter, we also want to go in and take a look at some statistics in the system menu. So I'm going to do that now. Okay, so I pull up System, and I'm going to go to Set Networks. I'm going to look at CAN settings. All right, and I'm going to look for the CAN OK status. And yep, CAN is OK. Great. That's what I wanted to see. So that's one thing I can check easily. The other thing I want to do is I want to go to the status menu and I want to take a look at what's happening from a status menu standpoint. So down here, you can see, if I scroll down a little bit, local network usage and all network usage. Holy cow, what is going on here? I'm using 30% of the bandwidth on this network, and all I'm doing is literally sharing 1 bit and 1 word of data. There's no way that's good. All right, I must have done something wrong. What could that have been? Well, on my slide, I think I mentioned one thing to check is that if the results don't make sense, especially if you're talking about bandwidth utilization that's way higher than it should be, check in your program to see if you've got a net put instruction that is flooding the network unnecessarily. Well, maybe that's what's happening with me. So let's go ahead, and I'm going to go ahead and fire up CsCAN next. And let's take a look and see what might be going on in my application. All right, so for those of you who were with me last week, this should look familiar. This is the program in the EXL6, which is sending the data to the network. So I've got a couple of net put commands here with always on type contacts in front of them. Now that doesn't automatically mean that every scan I'm going to be sending something to the network, but it could. So let me double check this here. So I'm going to double click on this net put function. And what do I see? Well, I see that, yeah, this function block is enabled every single scan, but I'm only transmitting on a change of state. No big deal, that's fine. So that data isn't changing right now, so it's not generating any traffic. So that looks good. All right, now let's go take a look at this other net put. Same thing, except, I forgot the change of state bit here. So every single scan, whether it's changed or not, I'm broadcasting this analog data to the network. I'm using up 30% nearly of my bandwidth available on the network through this one instruction that is poorly configured. All right, I'm going to go ahead and download now this change to this controller, and let's see what kind of difference that can make. Okay, let's take a look here. Oh, actually, I had a problem with my download. That's why we love live demonstrations. Let's go back to CsCAN. All right, CsCAN didn't notice the change that I made. So that's interesting. Let's go ahead and do another download, but this time, instead of using the smart load, which wasn't so smart this time, let's just go ahead and download the user program. All right. So when CsCAN uses smart load, it checks to see if there are any changes in the program, and then based on what's changed, it downloads what it needs to change. Now it told me that when it did the smart load attempt, it said there was nothing to change. So smart load wasn't so smart in that case. All right, back we go to our overhead view of our OCS. Okay. And again, things are still working the way they should. I can still change this data, and it's working. It was working before, though. Now let's go back to the system menu. Let's go to status. All right. And we still have big local network usage. So I screwed something up when I downloaded that. All right. Well, I guess you're just going to have to trust me that if you properly set the net put to effectively be a change of state, that it won't do that. But you know what? this is why we're doing things live. Let's just go ahead and find out what I screwed up. All right, I'm going to go back to CsCAN, and let's just take a look here. So here's the first one. Change of state. Yep, that's good. Here's the second one. Oh, I did not change it. Maybe smart load was smart and I was dumb. How about that? Let's say, okay, this entry field may not be blank. Okay, it doesn't like a blank entry field. Okay, so whenever you select change of state for a net put, it gives you the option of being able to trigger an additional communication or additional write or put, if you will, whenever another variable turns on, a bit type variable. Now, I don't want to do that in this case. I'm just going to go ahead and use always off for that contact. All right, there we go. I used always off. That's okay. So now that's changed. I'll go ahead and hit download again. All right. I'll go ahead and let smart load happen. See if smart load is smarter than me. All right, it should notice that I made that change, and then it should do that download. It is doing a download. All right, back to the overhead view. All right, the download is now complete. And let's go to the system menu. Let's go to status. And look at that. Net usage is basically 0, which is where I would expect it to be since we're not sending any messages, since nothing's changing state. So I'll have to go back and look at the tape and see how I screwed up on that first demo. So even a simple thing when you're doing live demos can go wrong once in a while, but that's half the fun. So that should hopefully give you an idea about what all is involved if you really want to take advantage of CsCAN in a larger system with a lot of nodes or a lot of distance or a combination thereof from a planning and installation standpoint. I'm going to go ahead and bring Casey back in. All right, Casey. So did you see anything I missed there?
Well, I think you caught it at the end, but no, no, that's it. I think that was it.
All right, very good. Yeah, I don't know how I screwed that up, but I somehow managed to not make that change that I thought I was making. So, you know, that happens.
Yep, absolutely.
You bet.
And no questions this week. I think you filled in all the gaps that people were looking for. So, a lot of information. That's good stuff.
That's true. And one of the other advantages of having this content available for later review is many of these folks watching may never have an application for CsCAN, which is really long or with a lot of nodes. But if they do, they can refer back to this video, in addition to, of course, user documentation and help files and things. But they can refer back to this video and the recording, and get that information that maybe they would have, slept on since they watched it live. Okay. So next week, we're going to be again, let's go back to the fact that every Tuesday at 2 o'clock, we have another live stream with another topic. Next week, I don't have the slide here for you, but next week we are going to be talking about another CAN network or CAN-based network. We're going to be talking about CAN Open. So this is our next 2-part series. Next week, CAN Open, how does it work? And then the week after that, we're going to be demonstrating how you might actually use CAN Open with an OCS. So in 2 weeks, we'll be talking about, or showing you actually, not a lot of talking, a lot of showing. We'll be showing you how to interface with a variable frequency drive. Many of us have interfaced with variable frequency drives over Modbus and Modbus TCP, but some of you may not have been aware that you could do the same thing with CAN Open. Also, we're going to show you how to interface a CAN Open encoder into an OCS. So let's say you have an application where you have more than just a couple of encoders. So you've exceeded the number of high-speed inputs on the back of an OCS. You want to add more encoders. How do you do that? Well, we're going to show you how to add an encoder over CAN Open. And CAN Open is a network which is set up to interface with encoders very well. Another thing we can talk about, which I'm not sure if we'll demonstrate or not, we might, is we'll at least talk about the fact that you can set up a CAN open stepper. So if you have one or more stepper motors that you want to interface with, of course you can do step and direction, which is kind of the old-fashioned way of doing it, but you can also interconnect them over a network, and one of the network options you have is CAN open. So we want to show you, we want to do more than just tell you how CAN open works. We want to show you practically what you can do with it with an OCS. All right, bringing myself back here, I want to thank you again for joining us today. I want to thank Casey for keeping an eye on the chat and for making sure that I wasn't screwing anything up any more than I already did. And then thanks again to Marcy in the background for keeping everything rolling on the marketing side. And until next week, we will see you and stay safe and have a great week.